Hi, let's solve this problem here given as part of the first period's exercises. The problem says that there is an applied moment of 300 Newton meters that is trying to strengthen a curved bar of square section of 3 centimeters and a mean curvature radius of 4.5 centimeters. We are asked to find the stresses at the inner and outer faces in megapascals. That means that we need to find the stresses in this point or in this area or in this area here. They're going to be the same along the length of the beam here. Okay. To start applying our theory or this Winkler-Bach theory that we have seen here, we need to know a few things first. And one important thing to notice is that we cannot apply the simple flexural formula given for straight beams into this problem. I said it before during the Q&A that I posted, but this is essential to mention here. There are certain conditions that we need to check beforehand in order to apply either the Winkler-Bach theory or the simple flexure formula. In this case, the conditions are given to apply the Winkler-Bach theory, and that depends on the depth of the beam in this case and the radius of curvature. We also need to be aware of something here, and that is what is the section that we're working with, and to know that this section is going to give us the parameters needed to construct the Winkler-Bach equations to calculate stresses in the upper face or in the upper surface and in the bottom surface here. This here, I have mentioned before, we saw it in the lecture notes. We derived the parameters or the necessary parameters for this type of section. And well, that makes it easier. You're going to see for the other exercise that I didn't give one of the necessary parameters to apply the Winkler-Bach theory, but it is easy to find. Is something that is already tabulated. You didn't have to reinvent the wheel in this case. That was easily found. You could find it easily in textbooks or on the internet. In this case, for this section, we need to make sure of something. That we need to know, or we need to have all this data. We need to have the length of each one of these sides of the beam, which we have because we are set that the the square section of 3 centimeters. So each D and B are 3 centimeters. We know what's the radius of curvature, and this is just dA, and dy is just a representation on what was given in the lecture notes. Now, what's going to happen in the upper face and what's going to happen in here? When this moment is applied to the beam to try to strengthen it, intuitively, I can know that in the top part of the beam, we're going to be experiencing a compressive stress, while in the bottom part of the beam, in here, we're going to be experiencing a tensile stress. If I wanted to write it using the terms given in the lecture notes, the compressive stress is calculated or is determined by this formula here, and the tensile stress is determined by using this one here. They're basically the same formula. The only thing is that we are just doing a little bit of rearranging the terms to kind of to consider magnitudes positive. I'm going to tell you which magnitudes we're going to consider always positive, but don't get troubled by this. In this case, when I take what I need or what are the parameters needed to employ my formulas into my real case, I will find that obviously D and B are 3 centimeters, the radius of curvature is 4.5 centimeters, and two new magnitudes that appear here that are not mentioned in this formula here, but sorry, in this representation here. These are D1 and D2. And D1 are simply the distance from this radius of curvature, the mean radius of curvature to the top surface, this part here, and the mean radius of curvature to the bottom surface. Now, you see that we are not taking any coordinate system here to say that, up is positive and down is negative. In this case, what I'm saying is that both quantities, D1 and D2, are taken positive. And that's why these two formulas here were rearranged, just two input values as positive values here. We could use the same formula presented in the lecture notes, but just taking into account the signs and no need to change anything. Let me delete some of this stuff. Now, this is pretty simple. Now that we have this, you notice that we are missing one term that we don't know what it is. That is this H2. And that H2 is associated with the shape of the section of the beam. Then we know also from the lecture notes that this H2 can be calculated by using the depth of the beam, D, and the radius of curvature. I apply using this formula here. When I substitute all the values, I get that this H2, this section parameter, is going to be 0.804. Now I have all the terms needed to calculate the compressive stress and the tensile stress in my problem. For the compressive stress, when I introduce all the values, I'm going to get that this stress is going to be minus 86 megapascals. And for the tensile stress, I'm going to find that this is going to be 54.1 megapascals. In this case, the compressive stress is the one who is going to dictate the failure, let's say the possibility of failure of the beam and of this beam. And this is let's say this is one of the stresses we have to pay attention to. This was basically the way to solve this problem. We answered what was asked in the problem. However, there is an extra step that I wanted to show you that is not requested by the problem, but it's kind of something to prove what was said or written in the lecture notes. And this has to do with the position or the location of the neutral axis. We know that when we have a curved beam, the neutral axis of this beam, which is the axis where the stresses are zero, is not coincident with the centroidal axis of the section of the beam. In this case, from the lecture material, we know that the position of this, let's say, neutral axis is going to be, or we calculated using this formula here. So it depends on the section parameter and in the radius of curvature. And we also said that this was always going to be below the centroidal axis of the section a little bit. And in this case, we find that that the position of the neutral axis for this case is minus 0.17. But how to visualize that? Basically, we have here the centroidal axis of the whole section, and then measured downwards, because it is negative here, I'm going to find the neutral axis for this case. And let's remember that this neutral axis, again, is where I don't have any stresses on the part. If I wanted to draw this on bigger, let's say, figure here, I'm going to have this mean axis, which is the mean radius of curvature, also is going to be coincident with the central axis of my section of my area, this face here, and this green one is going to be the neutral axis. So these two stresses calculated could have more or less a shape like this. I have a large compression on the top, and I have even large, but not as large as the compression, a tensile stress on the bottom. And again, this last slide was not requested by the problem, but it is interesting to show here. Now, it is kind of also something that is very interesting, that if you know what's the formula to calculate the compressive stress and the tensile stress in function of the depth of the beam, you could plot that. You could give values to certain, let's say, uh, points here. For example, you're going to know that whichever formula you use to calculate stresses, in here it's going to be 0, and then you can give this this point here, get a value, this point here, get a value, this point here, get another value using the formula for the compressive stress, and then you're going to have the correct shape of this stress here, or the stress distribution there. The same you can do for the tensile part here. And well, this is it. This is the way I want to show you how to calculate this. It's pretty simple on how to apply the Winkler-Bach theory. Just be careful about what section you are using, what are the parameters associated with that section, and then analyze intuitively which part of the body that you are analyzing is going to be subjected to compression, and which part is going to be subjected to tension. That's going to give you a good hint about which formula to use. And well, that was it. Thanks. I will jump in the next video to another example that was also part of the first period exercises. Thanks.